Hello, and welcome to this low-level JavaScript series where we're attempting to build the world's first RISC-V core on an FPGA using the TypeScript programming language. Now, this is episode 12 of this kind of sub-series, or I guess the first series within the journey, or however you want to call it, but we're on episode 12 of the project, and we're currently not yet building the hardware. I mean, if this is your first time tuning in, this is an interesting one to come into because it's sort of the end of this part of the journey, as you'll see. But if this isn't your first time, then what you'll know is that up until now we've been building an emulator. A really low-level emulator, one where we're actually modeling all the logic as register transfer level, kind of clock cycle by clock cycle, pipelined, actual kind of sort of hardware design that we would do on the FPGA anyway. And this is basically acting as the design document for the actual hardware side of the project. And it allows us to work out all this hard stuff, the actual design, without having all the added complexities of FPGA stuff on top of that. So hopefully what we can do is when we start working on the FPGA, we'll be able to transfer a lot of this over, and I won't go through the same sort of concepts of working out this is how this logic works, or this is how this. I'll try to focus on newer subject areas in that. But this part of the project, I could keep doing it forever, I think. I could keep improving things, and I could keep working towards more and more. But now we've actually finished, as of the last episode, all of the instructions that I want to implement. And all of the major concepts. I mean, there are a couple left over that I think would be worth going into, but I'm willing to actually put a line in the sand at this point. There is, however, one last thing that I want to do, and that's what we're going to cover today. And yeah, so we'll talk about that. I'll talk about what we're going to go into today, and what the next steps of the project are probably going to look like, the next few videos at least. Okay, so first of all, the problem that we're currently facing in the emulator is that there is one part that isn't really as it should be in the kind of hardware design sense of the word. It's something that is still very emulator-ish versus something that seems like an actual hardware design, and that is that the memory interface, our system bus, I'll kind of put a read request or a write request out on the bus and then something happens. That currently it's not modeled very accurately, and we can just take a really quick look at why that is and what that looks like. So if I go into the code, I open up the pipeline, and we go to something that accesses memory, so the instruction fetch stage accesses memory. The way in which we get the next instruction in our logic here is, well, we kind of work out what our program counter value is going to be here, and then we do this line, which is saying that our instruction value is the result of reading the bus as a function call. And this is just not how hardware works, right? We're talking about doing stuff clock cycle by clock cycle, and here we're doing a sort of magical, instantaneous read of the value. Now, there are some types of memory that we could... There are some memory interfaces that we could use, especially if we used onboard memory on the FPGA itself, on the fabric of the FPGA itself, where we might get one clock cycle memory reads and writes. But I actually do want to use larger memories and more complex memory devices eventually, and so this won't work for that. This is not a generic interface. This is very much a sort of programmatic, emulator-ish interface, which is fine for an emulator, but I think we might as well, take the last step and make it more realistic to the design. So what I want to do here is not that we are able to instantly read read from memory here, but rather that we issue a request to read from a certain address, and then some time goes by, and then we are going to receive a signal that says data that you read is now ready, and we can then look at that data and say, hey, this is what we got back from memory, basically. So we're going to issue requests out to the memory, and they're going to come back to us sometime in the future. And so we're going to need something a bit more complicated than what we have now. Not simply that if we enter the logic that we stall, and we're not stalling, rather, that we just perform the function, but rather we sort of have a state machine where we go through a couple of states and have to check that out. One thing you might notice here is that there is this piece of code in here which wasn't there before, which basically says if we get a reset signal in, then call reset. I made a small adaptation to the code from the last episode where we did the reset mechanism and the pipeline flush. Basically, I just took the logic that we had inline inside the RV32i class, and I distributed it into the pipeline stages themselves. So basically, I passed them a reset signal now. This should be pretty straightforward to show, actually. So now we actually pass each stage a reset signal, and it's just directly whatever the value of this trap flush is. And this is all we were looking at in order to call reset on all of the pipeline stages anyway. I find this just to be a more accurate way of doing it, right? We're linking signals together from different modules, and we're not kind of doing too much magical overseeing from the top. Okay, so a couple of things that we're going to have to think about here is, of course, that each stage we're going to have to introduce some more signals, of course, at least into the ones that actually do something with memory. We're going to have to build like some kind of state machine where we are in a state where we are ready to read memory, go into a state where we've read memory and we're kind of waiting for a result, and then when it comes back, we're going to be able to move back to our sort of ready state, so to speak. But one thing that we are going to have to change as well, that's also at the moment sort of not obvious, is that the RV32i class, that actually includes this block of code, which I wrote all the way back in the beginning and almost didn't touch. So here, this piece of code, what it basically does is it's in the compute, and we're going through and computing all of the stuff. We're running all of the stage compute and the CSR and the trap. And then eventually at the end, we're actually looking at our current pipeline stage and we're moving forward. And that is because now every pipeline stage only takes one clock cycle. So we can literally just move from one to the next in a counting way, basically. This is what this is, right? It's basically just a counter that wraps back around. And this would be fine, but now we're going to have stages that can take, maybe an unpredictable number of clock cycles, but maybe some will take shorter and some will take longer. And so because of this, we're going to need a new mechanism at this point to actually orchestrate that. So that's one of the things we're going to look at too. And the only other thing, because I kind of skipped over follow-up business, but the only other thing that I did in between was that I kind of extracted out the debug logic, which was inside. It was getting kind of big because I've been building up more and more debugging facilities. I put that into its own class, which is kind of just separate, and all the logic is there. And now the RV32i class is more or less just containing hardware stuff, and it does have this on breakpoint, so that when we hit a breakpoint from our debugging, we actually end up inside this class, so we can examine the surrounding state. We'll see that probably at some point. That is more or less it. So what I want to do now is to show a little design of kind of some of the logic and how I think this is going to work out. So what you see here is how I envision changing the pipeline from moving from one stage to the next. Instead of going like on every cycle, we're going to somehow need to signal that the stage is ready to move on. And so that's kind of what this diagram is showing. Here we have the pipeline stages. And they each have now a signal which we can call done or ready or something. I can't think of the best name for this, but let's say done for now, because this signal will be issued when this stage is kind of done with what it's doing. By the way, all of this only counts for the fact that the pipeline isn't parallel, by the way. If the pipeline was parallel, this wouldn't actually be as big of an issue. But I'm actually making extra work for myself here because I don't want to do the work of making it parallel just yet. So keep that in mind for while we're discussing this. So we're going to add this signal to each stage, done, when each stage kind of progresses through its own state machine, which says basically, am I ready to move on? Like, I'm in a stage where I'm ready, I'm beginning to do something, maybe I read some memory, so there's some latency going on, and then eventually I'm kind of ready to go back, and in that moment where I transition back to my sort of ready state, I'm going to issue a 1 clock cycle signal that goes high that says to basically to the orchestration logic, move to the next stage. Okay, so what's going to happen then is, for instance, in the beginning instruction fetch will be running, and then each of these kind of divisions is a clock cycle, let's say. So let's say it begins here, and we'll talk about why in a second, but let's say it begins here. It takes kind of 2 clock cycles maybe to read memory. Could be way more, could be less, but well, could be more. And then it's done, and so it issues this, on this clock cycle, it's issuing a high pulse. And then on the next clock cycle, I actually think these all should be spaced out by even 1 more clock cycle, because this stage needs a clock cycle to also see this signal. But try to look past that for a moment. So then the decode stage, it's not going to be looking at this directly, but the pipeline is some logic in the RV32i class will be orchestrating this and will basically say, okay, I'm going to run the decode stage next. It's going to do its thing. It's going to be able to do that probably in 1 clock cycle. And so then it's basically immediately done, issues its own done signal. And again, that moves on. We go to the execute stage. Probably that will execute in 1 cycle, but could be more depending on timing constraints. Then memory is going to be running, and again, that one may take multiple clock cycles. We might not need to do any memory access in that stage. If it's a addition instruction, then there will be no memory access, and therefore it could be done immediately. But let's say it had to do a memory read at this point, so that takes some time. Write back, that should take no time at all, so that's immediately done. And then we go back again and we're on instruction fetch. And there is kind of a chicken and egg problem with all of this, in that how does the very first stage run? How do we make sure? Because we don't want to have all of these have an active done signal, because then how do we know how to distinguish? So when we boot the CPU up, all of these signals should be 0, it should be false basically, we're not done. So we need something to issue, like to tell instruction fetch, hey, you should actually execute logic. And we have that we have like a pipeline initialization signal. And that will by default at reset be high. And when instruction fetch, when we're deciding whether to run the instruction fetch stage, we'll actually make a, we'll run this signal, pipeline init, and write back done. We'll run those into an OR gate, what you can think, we'll OR those signals together, and that will tell us whether instruction fetch is ready to run, basically. So I hope that is somewhat clear. And the only other diagram I will show you now is just, this is what we can think of as the memory access state machine. So when we are, by default, we're at the system bus now. We have to think of that becoming an actual piece of like hardware logic. When the system bus is in idle, which it will be by default, it's ready to accept memory requests, so it could take a write or it could take a read. It will then move into a waiting on read. So if a read is issued, for example, from instruction fetch, it's going to say, hey, I want to do a read, here's the address. That will begin happening. It will be waiting on the read until that read is complete. When the read is complete, which will take some time, then we're done. We can actually do some control signals to show back to the module that it's ready, and then we will go back to idle. So when we become a parallel pipeline, we're going to have to get a bit more advanced in how we orchestrate different pipeline stages wanting to access memory at different times, because both instruction fetch and memory access, they both want to access memory at different times, and so we're going to have to orchestrate how and when they're allowed to do it. But that's not really a problem for now. So hopefully this part is clear, and we can actually get in and start working on it. So I'm not sure what to start with first. I think so we could start with the state machines, or we could start by converting the system interface, and I think that's probably the best place to start. So let's go into the system interface. So as you'll remember, the system interface is this thing that implements a memory mapped I/O device, and actually all of the we had RAM and ROM, and we could have memory mapped devices, and they would all implement this interface, which has a read and a write. This is very much an emulator kind of design. You might see this kind of thing in like a game emulator for a game console, but we're going to have to change this, at least on the system interface level. So I think I won't go to the point of making the RAM and the ROM adhere to this same idea, because we can do it on the main level and just call that our sort of, we've abstracted, encapsulated at this point. So what I'm going to say is that this doesn't implement memory mapped I/O, because we're going to deviate the read and write a little bit, because read should now not return whatever the read was, and write should, well, write doesn't do that anyway. We're going to want to have some signals in here, and we're going to want to have a like register interface. So let's start out with that. To make a register interface, we can add a compute function method and a latch next. I think the simplest way to get some registers in this is we will add a register bank, which is this abstraction I wrote a little while back, and then that makes it pretty straightforward to add kind of a register interface to this whole thing. So what kind of registers are we going to need here? We're going to need yeah, and let's get let's add this already. We're going to want to have we're going to need like read complete, write complete signals. So basically something that just says, is the read or write ready to go? So let's have read complete. And the initial value for this will be 0. And then we will have write complete. And I think the rest we can kind of do internally. So let's also have a read value, because we're going to need to read something out. We can store that in a register. We don't specifically need to, but that would be fine. So yeah, let's do it like this. Oh, we can't call those like that because we have methods of the same name. So let's call this, let's just call this R and this one W. I don't normally make single letter variable names, but read write, relatively straightforward there, I think. So, and I guess we should add reset as well. Why not? Let's do it while we're here. So in compute, we can say, oh, this was, no, let's just ignore that for now. So in compute, what we're going to do is we're going to check if, I guess we need to get these in from the outside as well. So that's, yeah, let's do that quickly. So we take a ROM device around, okay. A little bit of maintenance, but a little bit of shifting things around is needed here. Let's make a system interface params type. We'll have these things coming in from the outside. So this, and then and what we're going to want to have here is something that says, like, whether or not, like, let's call it should read. It's a function, and we'll say it returns a number. That number will be 0 or 1 for true or false. I know I've actually used Boolean values elsewhere, and I'm mixing them up, but I'm okay with it. And then we are going to want to have should read, which is a function coming from the system interface params. Should read, should write. Okay, so if we're going to do a read, we can read that in like this. If we need to do a read, then what we can actually do is call this.read. We'll make these privates so they can't actually be called from outside. We'll say this.read value dot value is going to be this.read, and then I guess we also need the address. Let's just call it the address, and then we need a oh, that one should write. Okay, we're going to read from this address and the memory access width. Yes, that's another one we will need. And I guess we need a write value as well. So let's have address, we'll have write value, and we'll have memory access width. Let's call it access width. Okay, so then that's address, that's going to be access width, that's going to be write value, and okay, so when we read, we will then get the the access width. And the thing to note here is that, like, this is going to be the boundary where it's not realistic, right? I'm just moving now I'm moving the non-realism of the memory interface into this pot where it will be hidden away. But I think that's good from the perspective of, we'll also have something like this in hardware, whatever the boundary is with talking to a memory device, you know, it's going to be kind of hidden away inside that thing, and this is sort of our outside world interface, so to speak. So I'm okay with hiding it away into this point, kind of pushing the problem back by one layer, because that allows the design in the pipeline itself to actually be realistic. Okay, so that is going to be what we're going to do in that case. And then, of course, what we're going to also need to do is understand, like, what state we're in, right? We need to implement the state machine. So I also need to add a register for state. Let's make a system interface state enum. And we will have an idle state. We will have a waiting on read, a waiting on write, a read complete, and a write complete. And those should be our states. And let's just explicitly, even though this will be 0, let's explicitly and I kind of want to shorten this down. I'm going to call this bus state. I think that's just a little bit clearer. Alright, so in compute, let's actually, instead of doing that, let's switch on this .state .value. And this should be familiar from the previous episode and probably some of the other kinds of switching, state type switching we've done. I mean, in the last episode, we really explicitly built a state machine, so in this episode, we're going to be building quite a few more. Okay, so if we're in idle, that's where we're going to do the actual reads and writes. So if we should read, then we're going to read the value. So we're going to read the value and do some sort of like simulated time delay here. So we're going to read the value. Let's actually make a like a time delay or cycle delay cycles. Let's say we will delay for 2 cycles. I think that's fine. Let's add a state for delay cycles, which will start out as 0. So what we're going to do is, if we're in idle and we're going to do a read, we're going to kind of actually do the read here. Then we are going to say that this dot state dot value is going to be going to waiting on a read. I guess we should say that this dot let's do that outside. So like when we're in idle, no matter what we do, this dot delay cycles should go to 0, like because we haven't got anything going, so we can just explicitly set it here. We don't need to, but we can. And let's also set that read complete is 0 at this point, and also write complete is 0. So that's what that's what these values should be in this state always. Now reads and writes should be mutually exclusive, but so we should make this if else, but I think I'm just going to put it into if statements for now. No, actually I think I will make it that it's explicitly mutually exclusive. So should write, which means if you pass a read and a write signal at the same time, it will only perform a read. It will always do the read rather than the write. It's arbitrary. But yeah, you can't read and write from memory most of the time at the same time. There are types of memory where you can do that, but we're going to say that you can't. So if we're going to do a write, then well, we need to call the write function or the write method with the address and the value will be this dot get or write value. So we'll actually do the write here, and then we're waiting on a write. And then otherwise, nothing else needs to happen in the idle state. And then since we've moved into these two states now, let's make a waiting on read state. So what we're going to do here is we're going to say if this dot delay cycles dot value is less than delay cycles, then we will add 1 to this. And that's it. But if it's not, like if we have exceeded that or we're no longer less than that, then we can say this dot state dot value equals bus state dot read complete. And also in this moment, it actually, I'm wondering if we even need these read complete, write complete. We might not need these two actually, because we can actually make this signal go high at this on this same clock cycle, and then it goes low on the next one, and then the value should also be there ready. If that makes sense. Yeah, I think that actually works. Although, no, let's, no, let's get rid of those two states. We don't, it seems that we don't really need them because we can actually go to idle and we can just say that the read complete is now 1 in this stage. And this will be pretty similar in the waiting on write. We're going to delay for the same amount of time. We're going to go back to idle, but this time the write will be complete. I think that's our state machine. And the reason I think this is enough is because here we're always setting these back to 0. So in any case, this value should only ever be 1 for one clock cycle, because it will go high in this clock cycle, and on the next clock cycle it will go low. It will only ever be like 1 clock cycle high. And in that time, the value is ready. So yeah, the value's already ready here. So I think this is going to be fine, which is nice. It's always nice to get a simpler thing. State machines, yeah, it seems to be one of those things that you can always make simpler. They're always more complex when you don't think them through. So, what kind of values do we want to come out of this that can be read by the outside world? Well, we are going to want to have our read complete, write complete, and read value. Those are the ones, I think. So we will return this.regs.getValues object, and this takes a generic parameter which allows us to specify the named values that we're providing out, at least to the type system. It's kind of a hack, but read complete, write complete, read complete, write complete, and yeah, I'm doing this wrong as well. This is not, we don't need these here, we need this. Okay, I think that's this module up to date. Of course, everything's now broken, anything that references this, so fetch is going to be broken because this is not how we do it anymore. So let's already, at this point, start implementing our own state machine here. So export enum, and this is going to be the fetch state. So I guess we're going to be ready, like ready to execute. Let's just call this idle. I think idle is let's call it ready, because it's not that it's idle, it's not at any moment just idle. Okay, so we're ready. We're literally going to be waiting on a read, and then I think we need to have like a next stage. And you might wonder now why we didn't need this kind of state in the last in the system interface, and why we suddenly need a sort of additional stage here. And the reason is that here, unlike the previous stage where we actually did have the value ready on this go, I think what I'm thinking is because we have the orchestration stage, the RV32i kind of orchestrating this, we're going to be able to communicate that we are ready to go to the next stage. Let's see when we get to it, and I'll check that. But at the moment, I'm not sure I can properly. Maybe if I go to the thing here. So if we imagine this is the done, we're computing, and then we set this to high. Well, the way in which we're going to check the parent module of this can only see this signal go high on the next clock cycle, basically. It doesn't see it in this clock cycle because it hasn't propagated yet, hasn't latched. And so this goes high, and then on the next clock cycle the parent sees it and can actually tell the next stage to go to begin its thing. So what I think we need to happen here is that we kind of have a dummy cycle for each stage where it's not doing any important work, and the pipeline can actually sort of shift it, like shift to the next active stage, without actually sort of beginning the next instruction fetch, because we're one cycle off in the sort of propagation of this whole thing. And again, that's not a great reason, but I think that's going to at least allow us to have a serial pipeline versus a parallel pipeline for now. And probably when we make this parallel, we'll get not only benefits from being parallel, but also we'll be able to remove this clock cycle of latency as well. But I think we need it for now, so I'll leave it in. All right, so we're going to have a state. Let's add that. State that start in ready state, and it's going to be really similar kind of thing. Well, I guess we're going to need a couple more signals than this as well. We're going to need read request. I guess we'll just call it read here. Like, we don't need to call it anything else. We're going to have read, and we're going to need the address. The address is just the program counter, so we don't need to do anything special there. So we're going to have read, and then we're going to need to bring in some values. So we're going to have read complete, and we're going to have read value. All right. Okay, so we've got those. And these are also going to be the most kind of these are going to be the most complex of like the fetch stage and the memory access stage. They're going to have basically identical logic in this way. I guess the memory access stage is going to be slightly more complicated because it also has writes, but it won't be that different. One of the things we can actually do is get rid of the fact that we need the bus here, because we don't need the bus at this point. So let's just get rid of it already. That's one less place where we'll be able to make a mistake. And then, so reset, that's going to take priority over the checking the states. So if we're resetting, we're resetting. And if we shouldn't stall, then let's switch on our state. If we are ready, then we're going to want to get our next program counter value, just like always. And we can't read an instruction value yet, but what we can do is to say this dot read value is a 1. We're going to want to do. We're always going to be wanting to initiate a read request at this point. Then we are going to go to the waiting on read state. We're going to need a break. Actually, I've just realized that the system interface needs breaks after all of the cases. Here, here, and here. Of course, we don't need that in actual hardware, but we're still programming in programming languages here, so we need breaks. Otherwise, we're going to fall through because of switch case legacy. All right, so that, I think that takes care of the fetch, the PC. Let's also explicitly say that oh, we don't have that yet. Yeah, we're not dealing with whether or not the next stage should be ready. So we'll tackle that part after this. Let's focus on the memory itself for now. So if we have if we're waiting on read, then we can check if the read is complete. If the read is complete, then the instruction value the instruction value is going to become the read value. And you might think, oh, that was a function call before and now it's another function call, but this is just the mechanism for getting in a value from outside, right? A function call is a way of getting the latest value from somewhere else. But presumably this latest value is something that is going through our register system and is a latched value clock cycle to clock cycle. So it's not changing, it's not something magical. This is just getting a connected value from outside. It's just the way we've built that here. So here we get the instruction, and we can say this.state.value is going to be next stage. And let's break at that point. And then in next stage, then we're going to, well, we're basically going to go back to the ready state. That's it, I think. Read value, read complete, everything else good. I think that's all we need to do here. Memory access. So we're going to need to do pretty much the same kind of thing here. So let's see if we can copy some stuff already, like the things we'll need. We'll need read value, read complete. We'll also need write complete. And we won't need the bus. And one of the other things is the states. I think our states are going to be pretty similar. We're going to be having waiting on read, waiting on write, and next stage. And that should be pretty much it. So we won't have bus. We will have read complete. We'll have write complete. And we'll have read value. Yep. And then we'll get rid of that. Okay, so now we need to change this up. This is going to be a little bit more hairy, but hopefully, again, still not that much. I want to leave this kind of stuff, like anything where we're just assigning values, like that we got in from the outside, we can leave that outside of our state machine check. Like all this stuff, or checking if we're unaligned, access width, write back value valid, all of this kind of stuff we can leave outside of the kind of state check. But we don't even have a state register yet. Let's do that first. So, if we are ready, then we basically need to do all of this stuff, like checking if it's a store, like basically all of the stuff that's in here now. Not quite all of it, but most of it. That's going to go into here. Okay, let's also trim all of that down. And now what we're going to have is that, like if we're doing a store, for example, we're going to switch on the access width, and then we are going to initiate a bus write and doing those kind of things. So obviously we're not going to be doing this at this point. Instead, we're going to be signaling that we want to do a write, which means actually these additional signals, yeah, we didn't take those from fetch, but fetch has its own just read signal, which is just here. We're going to need a read signal and a write signal. So here, instead, what we're going to be saying is, and actually saying this as well, I think we don't even need to switch on the access width at the moment. Oh, only that. No, we can leave it like this. Okay, so we're going to say this dot write dot value is 1, and I guess we're going to need a write value here as well. We need to transmit the value we want to write out, and we're going to need to transfer the access width out as well. So here we're computing access width like as a thing. Let's just put this on this dot access width dot value for now, and then we can use that as a sort of combinational kind of value by just looking directly at the next value. So here, I'm going to be doing that here as well, and down here. Okay, so we're going to write a value. The access width is already set, and the value, the write value, that's going to be the low byte of RS2, and then we can get rid of that. And then at this point, I guess let's actually do this kind of outside this switch statement, because this will be common to all of them. So or we do it before. So write will be 1. The value here is going to be set like that. FF. Okay. So I think that is our store. Yeah, I think that should be our store by default. All right, then we have load. We're doing an on a lines check there. We're going to need to do that in store as well, but we do an early return. I'm going to again leave that kind of stuff for now. Should sign extend. Yeah, this one. This should be fine, actually. Also, this could be outside. Let's put all the stuff that's like just pre-computable outside. So here, now we're actually like recording a value, but actually we just need to administer the request. So this is going to get a little bit, like basically this logic is going to move into the read complete. So let's actually maybe like just flesh out the last parts of, let's flesh this out. So in the case that we're in memory access state waiting on read, we'll have waiting on write, and we'll have next stage. So in the case that we're waiting on a read, like what's here, what is going on here in this part, I think we're basically going to move that here. So if our access width is byte, then yeah, we're going to be doing that. We're also going to need to check. It's not quite complete yet. So what would we be doing here at this point? We're going to be saying that we want to perform a read. So read.value equals 1. And the address that we want to read from, that's a good point. What is the address? Oh, it's actually pre-computed here. So the address we want to read from, oh, we don't have a signal for address. Then I guess we make address a first class signal as well. Yeah, that makes sense. And again, this should be done in the ALU. So this dot address value, and then so here the read, the address is already written. Yeah, the address is written. So I think because of that, yeah, I think that's it. I think that's all we need to do. Because we're not... access width is also already taken care of. Yeah, this should be it. Actually, the other thing I forgot to do here is that we should also be changing state at this point. So our state should be going to waiting on a store, so that's a write. And in load, we're going to be waiting on a read. Okay, now for load upper immediate, like we're just using an immediate value, but we do need to change state here. So we do need to go to next stage at that point, and that's going to be the same for this one. Wait, where am I? Going to be the same here. It's going to be the same for if we're dealing with a system instruction. The CSRs, we're not concerned about those. They're not part of this same interface. And add upper immediate program counter, same. Okay, so that takes care of that. If we're waiting on a read, the value, well, that's just going to be the value that we read at this point. But we do need to, and it should come back as a byte, and whether we sign extend it or not is going to be dependent on this. So the only thing we really need to do is to say this.read value. And actually that means we could do it out here. because it's just the register. So let's get rid of that. Let's get rid of that. And let's get rid of that. We don't even need that anymore. And we only care if we're sign extending stuff. We're writing back this value. And we are also progressing to the next stage. To the next state, rather. But we're only going to do this if it's actually ready. So if this.read complete, then we're going to be doing this stuff. Otherwise, we're just going to stay in this. Otherwise, we're just going to stay in this state. If we're waiting for a write, the only thing we actually care about, we don't need to do anything with this information. The only thing we need to do is to move the state forward to the next stage. And in the next stage, the only thing we need to do, and we need to break. I did break in the last one, didn't I? Yep. The only thing we need to do here is to, again, move state forward. Okay, so that was a bit trickier, but I think that's also all the logic that we need for this state machine. And I think now, well, now we actually need to go and, even strangely enough, we need to go and make all of these other stages also state machines, even though they don't have memory access, because they're going to need to progress this thing forward. But before we do that, let's just let's actually fix all the bugs that are going to be here now, because we're not actually implementing this, all this stuff after changing so much. So that's ROM. ROM, RAM, and then we're going to get a bunch of these signals coming in. So, access width. We're going to be getting that from this is going to depend on where we're reading from. I think this, so we're wiring everything together here now, and we've got a couple of places that we could read from memory from, the instruction fetch or the memory access stage. So what I think we can do is we can just like look at the instruction fetch stage. This should be a function. Yeah, so this.if dot, and I think the problem here is, yeah, this is also come across this problem before. So we want to get the instruction values out, and are we not exposing these signals from fetch? I guess not. Yeah, so which ones do we have? We have, these are coming in, the read signal is coming out of here, and we just need to add it here. Then, so access width, this is going to get too long, so we're going to need to do the same thing here. Okay, so if the instruction is reading, and just return memory access with word, because we're always going to read 32-bit words from here. What's going on here? I think the problem is just that these are not implemented. Okay, so if we're reading, then it's going to be this. Otherwise, it's going to be, and it also didn't take these from memory access. We also need to expose all of these. So basically, if I guess we could do that like this, just to make it a little yeah, maybe it's fine. Okay, so basically, if we're doing a read, it's always going to be 32 bits, so we do a word, and otherwise we'll just take whatever we got from memory access. And if this is valid or not, it doesn't matter that much if it ends up being like, if we're not supposed to access memory at this moment and this is some junk value, then it doesn't matter. Okay, the address. This is again going to be dependent on who is who is reading. So in this case, we are going to want to read more than one value out of here. So let's just put it up like that. So if instruction fetch is reading, then it's going to be the PC, and otherwise it's going to be the address here. Whether we should read, we can actually just OR these signals together. Should write will just be if this one is going to write or not, and the write value will be this. Okay, so that's all the wiring done for the bus. Then we need to do this. We're not going to take the bus in. We are going to take read complete. This dot bus, and here we need to expose some values of the, yeah, let's change that as well. Read complete, the read value is going to be the same. So that's that, and then memory access, again, take away the bus, read complete, well, actually these ones will be the same, so throw those in, and then write complete. All right. I think that's it. I think that's the wiring for that done. I'm sure I'm making a mistake here. I'm writing a lot of tricky code. So I'm certain I'm going to make some kind of mistake along the way. But let's just plow ahead, because the rest of these instruction stages, pipeline stages, they also need to become state machines. So let's go straight into the code. Let's add export enum decode state, and we will have a ready and a next stage. This is going to be the interface that the rest of them have. We'll have, let's just add a, state, which will be ready, and like everything that's there now is just going to become the ready state. So this.state.value, in the case that we have decode state ready, do all of this stuff. We need to indent quite a bit, and we need to break at the bottom. And the thing we need to insert into every stage, including the ones that we've just come from, is also going to be next stage ready. Or we could call this stage done, not state done, let's call it stage done, which would be a 1-bit signal. This is the done signal from this diagram. And stage done is going to go high. Because we're always done here, let's just do it right in the beginning. Like the stage done goes to high. And then the state goes to next stage. And then in decode state.next stage, the done goes to 0. The state goes back to ready. This is it, I think. And we need to expose, what was it called? Stage done. Yeah, it could also be called next stage ready, like we're ready for the next stage, but I think just saying that this stage is done is also fine. Okay, so that's decode. Let's also put this in fetch, since we don't have that. So stage done, and if we're ready, then we're not done. Here we know, here we can actually write this dot stage done dot value equals 1. Here we can set it to 0. And then what's going to happen is we're going to say that the stage is done here. It's going to take a clock cycle to get propagated to the logic of the parent module. On the next clock cycle, we're going to be here. We're already going to be saying like, okay, set this down, go back to ready. And then on the next clock cycle, we're going to go back to this state, but we're not going to be executing this stage anymore. So we should be safe. Same thing for decode. So we have fetch, decode, we need execute. Let's copy some stuff from decode actually, just to try to save a bit of time here. Let's memory access, execute. So we're going to need a state. I liked it with state variables. I like to be explicit about which state they are in, because I want to think of this being, this is the reset value basically, right? So I want to be really explicit that like this is the state that we begin in. So we're ready, and the stage done. That does not begin with execute ready. Decode. We actually also need to add, oh, that's done here. In fetch, I probably didn't do it yet. So now that's covered there. Execute. So again, maybe I can copy some of this again from decode, just to try and be a bit, I know that this was actually faster, but it's fine. Case execute state dot ready. I don't know what's happening. In the case that we're ready, we're doing everything that we do normally. It's funny that sometimes it indents correctly and sometimes it doesn't when you paste into something like that. Okay, and we'll again immediately just say this dot state dot value is going to be the execute state dot next stage, and this dot stage done will be 1. So then we need the second case. I read a tweet recently from Andrew Kelly, who was talking about a hot take that sometimes typing speed is actually the bottleneck, and I'm really feeling that today. Okay, memory access. So memory access, we've already got our state, but what we need is our done. Let's put that. Where is the state actually? Oh yeah, it's up here. So this is going to be stage done. And when are we done here? We're done. We're going to be done whenever we're also done from these waiting on read, waiting on write. So now the tricky thing here is that we need to remember to actually also go back to this part, and on these other kinds of state transitions, we also need to be done on these ones too, where we don't do memory access. Okay, and then just write back. Write back's a nice simple stage, so there's also less noise, which makes it a little bit easier to see what we're doing. I'm getting tripped up writing the word state versus stage now. This one didn't actually have any registers. This is going to be our first registers. So this, so we're going to have state is this dot add this dot regs dot add register state, and that will be write back state dot ready. And then this one is going to be stage done. Alright, so in compute, nice and easy. Really on the home stretch here, and then we can test this out, change the mechanism for moving the pipeline forward, and then test it out. And then I think we're done. It's actually taking much longer than I had originally anticipated, but we are almost there. So it's going to be this logic, and then this dot state value is going to be going to the next stage. This dot stage complete, or stage done rather, goes to 1, and we break. I've probably forgotten a break somewhere. And if we're in next stage, this dot state value goes to ready, and this goes to 0, and we can also break. Latch next, we should actually call this dot regs dot latch next, and let's add get write back values out, returning this dot regs dot get values object, and we're only going to have the one thing here, which will be stage done. Alright, so that's that. So now we can actually move down to this point where we actually move the stages forward, and this is going to tell us, like, when we're in a given stage, if we can actually move forward. So if we're in instruction fetch, basically what I think we're going to need to do is add an if statement to all of these things. So maybe what I'll do already is just like, put these on a new line. And what we can do here is we're going to do this if this dot if get instruction values out dot stage done. I mean, I think that's it actually. So basically we want to wrap this if statement around all of these, adapting for the values we need to get out. So in this case, and this actually, I almost made a really big mistake here. So we need to look at like the previous stages, result, and that's how we know. Like, wait, no, no, I'm wrong. If we're in instruction fetch and instruction fetch done, then we can move to the next one. Yeah, I was right the first time, but yeah. Okay, so if we're in decode, then we're going to want to get our decoded values out. If we're in execute, then we're going to want to get the execution values out. Apparently in execute we didn't return stage done. Alright, and then finally, if we're in write back, and here in write back, we do a little bit more. Now the thing here is, yeah, actually, I spoke about this this PL signal, but actually I don't think that's going to be needed because we're actually going to start out being in the instruction fetch stage, which means we're going to run the instruction fetch logic. So I actually don't think we need this pipeline in its signal at all. If I just look at this now, I have the feeling that we're just going to execute our instruction fetch stage because we're going to be in that point. And if I look up here for like when stages themselves are active, it's going to be when the pipeline stage is on that stage and when we're not stalling for some other reason. So yeah, I think we're good. I guess let's test this out. Let me take a look at what the program we have is. So that's this part in main. Yeah, I think we should be able to see what's going on if we just chuck a breakpoint in. So here we can just add breakpoints basically in the same way, right? We just say rv debug add breakpoint by name. So I moved all of these debug related things inside this debug object, which is a breakpoint debug class. We don't really need to look at it. Let's try it out. So I'm going to run this, and I'm sure that I would have broken something. Apparently there's a debugger there. Okay, so that didn't work. We stayed in the instruction fetch stage, and also it didn't ever go into my breakpoint, my breakpoint thing. Huh. Okay, well let's just put an actual breakpoint in and see what's going on. So breakpoint and play. So okay, so it's not actually putting the breakpoint in. That's really annoying, but okay. I'm having trouble at the moment. I'm not sure why, but I'm having trouble lately. Let's just try doing this. I don't think this has anything to do with it, but I'm having trouble with being able to set breakpoints and have them actually catch. Okay, that one worked, but alright, so what should happen is that we should, well, we're not stalling, so we're not going to do any of this kind of stuff. But if we're in instruction fetch, we should be looking at our state here. So we're going to get our PC. We're going to say that we're going to do a read, and we're going to move to waiting on read. So that's that. Then what we're going to want, oh, I think I know what I've done. I added a compute to the bus, but I don't call it or latch anything, so we didn't have a hope of being able to see anything happen then. Alright, so let's try that again, I guess. Let's just see if we get somewhere with it. Okay, now I have the feeling that I know why we're getting all of these out now, so that's just something we might need to fix. because I think we're seeing it for every pipeline stage. No, apparently this is just messed up. Yeah, okay, so it's not quite working. The reason I think that we're seeing that repeat every time is because when we're in instruction fetch, like we're assuming it only is one clock cycle, so we can print this out. So we only really want to print this out on the first clock cycle of instruction fetch. So what I think I would do just for this part of the debugging is I will make the state of this not private, and then we'll just peek into it from here. So if we're in the instruction fetch stage and this .if .state.value is and this has to be fetch state. If we're in the ready state, then we'll do that. And I think we'll, at the very least, even though it's going to be broken, we should see. Okay, so we see that we log out here, jump to start, and then here we're in start, so that's a good sign. We actually made it through one instruction. We get to load upper immediate, and then somehow we end up going here. Yeah. So what's that all about? So I think, I don't know actually at this point. Let's have a look. So how can we test this out? Like, we can put a breakpoint in here, presuming that it actually works. It seems to just place my breakpoints. Okay, so at least that's now there. So we should be here at the end of like here we're breaking before we execute this instruction. Oh, okay, so we haven't executed this yet. In that case, maybe we want to take a look at it. We know it's a load upper immediate. Maybe we want to see what's going on at the decode stage. So let's just go to decode and put a breakpoint and end up there. Alright, so we're already going to the next stage. We're saying that this stage is done. That stuff seemed to work quite okay. So it should be a load upper immediate. Shouldn't be either of these two. So we should be, is load upper immediate next value 0? That's interesting. So what does it think this is? It thinks it's still a jump. Somehow we've ended up with the old instruction value. Yeah, that's what it seems like right now. It seems that we've, at least if the debugger is to be believed, and we haven't actually executed this yet, but I think we have. And we can test that out again by putting another one in decode. Because this breakpoint is moving. So here we're in decode, and this should be a jump instruction, and we should see the jump address. Is jump next value? Yes, it's a jump. And the immediate is going to be the J immediate. So what is J immediate? 368. OX170 is presumably 368. Yep. Okay, so that looks good. So we're here on breakpoint because we should be breaking on the first instruction. Now we're back here again. And again, is it a jump? Apparently it is. And maybe we'll see J immediate as 368 again. So it seems that we're just receiving those same values in again. The program counter is moving. Well, no, actually, the program counter must be moving because it is reading this this value. Wait, do we see that program counter also in decode? Because we have it here. Program counter. So it is pointed at this instruction, but somehow instruction fetch is messing up at that point. So that should just be the next place to look. We'll do a restart. Yeah, I think what we want, the debugger, I really don't know what happened to it. It just sort of one day stopped working, but I think we can solve it like this and then kind of manage the breakpoints manually. Okay, so we're in ready, and we're going to get here. Eventually we're going to end up in here, presumably, which we do. The value should be, or of course the value itself will not be right, but I don't know what this is right now, but it's probably correct. Maybe we can just make a note of it. So this dot instruction dot next value, so we can see it here. So what I think is going to happen is that somehow we're not maybe we're pulling in the branch address, because we should be adding to the PC here, but okay, so we're in the ready stage. We didn't actually put one down here, but we're in the ready stage. And the PC next value is 170. I think the address is not getting updated in the system bus. Okay, apparently this has crashed. Oh no, it just tried to open a file. Okay, so in the system interface, let's take a look at what's going on here. It certainly seems like, okay, before we do that, the address, you know, I think I might know what the problem is. Yeah. No, I'm not actually entirely sure. But okay, let's put a breakpoint in here. So at some point, Wait, how is this read complete then? If we didn't... And of course all my breakpoints have moved again, so let's just close some of this stuff down. So let's put one in here, one in here, and one in here. And we can also put a breakpoint down here, one in here, one in here. Okay, so at this point, we shouldn't read, we shouldn't write, so we're done. Here we're waiting on a read, so we've pulsed our read high. Read is not complete. This time read is high, so we're going to read a value now, so we're going to try and get the address. The address that we want to read from is here. If we run that, that is the first instruction, which makes sense in this case. Access width should be fine. I'm not worried about that. State value waiting on read. Here we're still waiting on a read. We don't have it yet. Here we're waiting on a read. Delay cycles is currently 0, so we add 1 to it. Then we're done here. Still waiting on a read, not done. Delay cycles not done yet, add 1. Still waiting. Here now we're done, so we're saying our bus state is idle and that the read is complete. We end up back here, so I think we should go in this time. So the instruction value, we're going to read the value out. We're going to the next stage and we're saying stage done. Here. So the read is still high, it looks like. Whenever we do a read, yeah, that's really dumb. So these signal values need to be updated. Read needs to be 0 in this case. Let's just make it 0 actively. This is one of those, this is a good reason for why you should always explicitly set every value in every possible branch case, even if you think you don't need to, because also in the hardware definition you don't need to, but it's going to take on a value and it's better to be explicit about it. Let's make sure we have done this properly in memory access. So in memory access, we've got our read and our write signals, and they can potentially be high in the ready state, but if we're in waiting on read, this dot, and actually I need to check fetch again to make sure I did that in the right place, because that should always be done. This dot read dot value should be 0, and this dot write dot value should be 0. The rest are fine. I think we don't need to worry about the other parts. Okay. All right. So that was definitely a bug. Let's see. A whole bunch of useless breakpoints now. Okay. It's slow debugging, but it's looking... wait, we're just locked up somewhere. Okay, so when it did add upper immediate, we seem to just jam up somewhere. Not quite sure why. Add upper immediate. and then there it just gets stuck. So what's happening at that point? My inclination is to check memory access at this point, because this is the... Well, that's not true, but this is an instruction where... Let's see what happens. Do we even get to this point? Yes. We do all of these things. And in this case, it's going to be a load upper immediate. Oh no, it's not. It's going to be none of them. Oh, yeah. In the case that we're not doing any of these things, then we also need to make sure that we update the state and the stage done. Otherwise, we're going to stay in this stage forever. This is why we write an emulator. Can you... Maybe you can't imagine because you haven't done it at this point, but these kind of bugs, this series of stacked bugs, trying to debug this on hardware, well, I mean, probably we would do it in simulation, but trying to debug this like on real hardware, yeah, this would take a lot, like many hours longer. Okay, so now we're getting somewhere. Now we're just running code. And at some point we should... Oh, we crashed. Okay, where did we get to? We got to B8. And B8 is... if we use RISC 532 obj dump main, B8 is here. It's a load. Okay, so it's a load word, but I feel like we did more load words before that. But okay, let's take a look at it and see what... Hello there, I'm coming to you from the future now. You've just seen me encounter a bug, and in this video it's going to take me a while to actually find the bug, and so I'm going to cut to that moment now. Normally I like to leave the debugging sessions in because I think there's quite a lot of value to be gained from actually not only understanding the code itself, but also the process of figuring out and finding where your bugs actually are. But in this case, I think the video is quite long already, and in the interests of saving you time, and also that there has already been some debugging in this video already, I feel like it's okay to skip ahead. So we're going to be jumping ahead to the moment I actually find it, and you'll see what it was. So we'll get to that right about. Okay, so we're in load upper immediate, memory access. Write back value valid should be true. It's a 1, it's true. Load upper immediate, write back value immediate 32, so the next value here is that. We're done with this stage, we're going to the next stage, and then we're in here again. The write back value valid true should still be true. We haven't changed anything there. And we also haven't modified that register, write back value. Oh wait, we have. We set that equal to the ALU result by default. Yeah, so we should not do that. We should not do that in this case. We should only do that if we're ready. Alright, that is going to make a pretty significant impact on this, so maybe let's fingers crossed that's our only bug. Alright, let's take a look at the stack pointer at this point. This.reg file 2 with value. Yep, that looks good. Okay, let's get these out. Jump and link, copy initialized vars. 8.8, this was a problem before. We get through it. Made it through the loop, jumping into the main function. Now we're doing main function stuff. Jumping into the equal handler. Returning eBreak. Alright. That was a rather intense debugging session. And of course it was a stupid mistake. Again, one that would have been really hard to find in hardware, and I'm really glad that we have a debugger to help with that. But still, tricky stuff. But we actually now have a memory interface that can take multiple clock cycles, and that actually makes sense, right? We're communicating between hardware modules by signaling rather than calling functions. And with that, we actually have a complete working emulator. There are a couple of things that I did want to put into this, and that maybe I still will work on in between and maybe just show the results. One of the things I wanted to do was to implement the timer interrupts, because although we did exception traps, we didn't do interrupt traps. And I mean, there's not that much difference between them in terms of imagining how that might look within the code. But still, I thought it would have been an interesting one to go into. I'm okay with skipping it because we will do it in the hardware, but we might revisit that in the future. But my current plan is to skip that for now. Another thing that I am probably going to do in a live stream in the next week or couple of weeks, we'll be adding waveform view, adding a waveform view to the emulator. And what I mean with a waveform view is that well, we're looking at like this kind of thing here. These are kind of waveforms, right? We have a signal name, and we see time progressing, and we see when the values change and how they change. There is a well-known standard for this that's used within FPGA simulation and ASIC simulation and all that kind of thing. There's a special file format, and I think, well, I know for sure because I already have done it in the background, but I know that we can implement this waveform dump, basically, where we can run the processor and then just view all of the signals across every clock cycle and which values they had and how they changed. And that is an amazing debugging tool. That really will make a huge difference to debugging. It won't necessarily help you find a bug like this, because this was just a line of code being in the wrong place, but it does help you figure out certain kinds of bugs. And I'm certain that if I were to add that right now, that we would find even more bugs that I just haven't found in the testing. So that's something to look out for if you're interested. It will probably be on a Friday or a Saturday evening, European time. But I'll let people know about that in the Discord and on Twitter. So if you can find links for those below. If you're interested, you'll find those there. Now, the next steps for the project. Well, of course, I want to actually get into hardware from this point. And all the way back in the very first initial planning video that I showed in this series, I talked about implementing UART as kind of a starting point, because UART will give us a debugging window. Basically, it gives us the ability to do console log from our processor. And what that will be is that we'll basically have a memory mapped register somewhere inside the CPU that we can write a byte of data to, and it will output that byte of data in a format called UART across some electrical wires, basically. And we can connect those wires to a special USB device which takes UART and turns it into USB, connect that into the computer, and we can see those bytes print out across the screen. Not only that, but we can also send bytes to the processor, which can make a good way of loading programs into the CPU. So that's one of the first things that I want to build, will be a UART module. And not only a UART module, but then also something called a FIFO, which is basically a queuing mechanism, so that you can push data into this thing, ready and queue it up faster than you actually can send it out, because UART is not particularly fast. And when we are running the processor, it's going to be able to run quite a bit faster than we can actually send or receive data. And so in order to avoid having to just wait on the spot until we have a spot to actually send or receive data, we can actually, you know, generate the data a little bit faster than we can send it out. So that's going to be the first port of call, and then we'll begin implementing the CPU itself on an FPGA. And in the beginning, I'm still not 100% sure which FPGA I want to use. I might use the Icebreaker board that I have, which has a Lattice up 5K, quite small, not particularly powerful FPGA on it, but it is fully compatible with all of the open source tools, and thus it will make it easier for people to replicate, for one, but also it will make it easier for me to stream this stuff out, because if I use the Xilinx board that I'm planning to use, well, because I think it's a better fit in general for this project, then I'm going to have to, one, learn quite a lot about the tooling that I don't currently know, and and two, I'm going to have to figure out a efficient way to show that on video, because I have to run a virtual machine and a program that's going to take quite a lot of resources. But we'll cross that bridge when we come to it. I want to say thank you for watching. If you've managed it to this point, if you sat all the way through that debugging session, especially if you saw the bug earlier on, then, well, thank you very much. Even if you didn't make it all the way through, thank you very much for watching in any case. Thanks to all the patrons of this channel, and I'll see you in the next one when we really get started.